Muy buenas tardes a todos, bienvenidos al seminario de investigación del Departamento de Ingeniería Industrial y el Medio de Investigación Operativa. Hoy día tenemos el placer de contar con Thomas De Munck, alumno visitante del Doctorado del Center of Operation Research and Econometrics de UCLouvain, quien presentará el trabajo. Thomas is a PhD student in the Operation Research Center in Econometrics of UCLouvain. He's a member of the Research Project Platform, Regulation and Operations in the Sharing Economy. He will present today, and he'll present in English, the work Dynamic Pricing and Dispatching Rider Sharing Networks, a transfer reinforcement learning approach of work from Professor Chevalier and Chris. Thomas, thank you for your time.
Yes, thank you. So, first of all, I would like to thank Jorge Vera for welcoming me here in Chile. Given that we are not so many, please just interrupt me if you have questions and we can make it a bit more interactive. Okay, so during this talk, I will talk about ride-sharing platforms, and hopefully you will understand a bit better what are the main issues with managing these platforms, such as Uber. And you will also see several approaches based on reinforcement learning, mathematical optimization to address these problems. So I will motivate the problem, then I will present you a Markov decision process model with pricing and dispatching decisions. Then we will explore the different solution approaches that we can use to find a good policy for that model that is based on mathematical optimization and deep reinforcement learning. And finally, I will show you some numerical results based on these approaches. So ride-sharing platforms, as you know, are nowadays ubiquitous. You find them in all the major cities in the world. It's very present here in Santiago, for instance. And here are a few statistics and a few companies. But these platforms have several issues that they need to manage. And for me, there are three main issues that I will try to address in this presentation. The first issue is that the demand of this platform is heterogeneous in time and space. So here is an example in the case of the island of Manhattan. I plotted the realized demand from Midtown Center, which is that zone here, to the distributed per destination during two peak hours, during the morning peak hour and the evening peak hour. You see that you have not a lot of demand during the morning because it's basically the destination. But in the evening, you have that huge peak in demand in Midtown, mainly going back to the home of the people, to East Village, Upper West Side, and so on. So that's the first thing that you need to manage. The second thing is related to the supply, because actually when you serve customers on these networks, you have to be careful because it will affect future services. Meaning that when you serve a customer, for instance, with that driver in zone 1 in time 1, that driver won't be available for the subsequent time periods, and it will become available again in another location. So you need to manage those interactions in the network. And here it's a simple example with two drivers, but now imagine if you have 1,000 drivers. And that the travel time is stochastic. Now, a third complexity with these networks is that actually the drivers are not simple resources. Sometimes they don't find customer in a location, so they decide to relocate to another one, and it will basically disrupt what the platform may have anticipated. The same goes with the customers. They are very impatient, so they don't like to wait, and they may cancel an order. Okay, so to summarize, you have heterogeneous demand in time and space. You have the fact that the customer service at one time will impact customer service at subsequent times, and you have complex behavior on these platforms. So how these platforms have addressed these issues? The first one that you know is probably know is dynamic pricing. So the idea is that you increase the price in a location when you have a imbalance between supply and demand. You have two effects. You have a local effect on the demand into location, and you have a global effect on the supply in all the locations that may decide to relocate to the location, because the drivers see on their heat map where you have a price increase. Now, a second way to address this that is maybe less known is that those platforms also optimize driver dispatching. So they don't match the drivers only with the nearest customers. Typically, they wait some time so that you have a higher market thickness, and then you match the customers with the drivers. Also, sometimes the platforms, when not sufficient drivers self-relocate by themselves to a location, they propose, hey, we can pay you some money if you relocate to that location. That's the case with Lyft, for instance. So in my model, I will try to capture those three issues and to include those three types of controls for the platform. Let's go to the model. So here is the general problem setting. You have a set of locations, for instance, neighborhoods that you need to manage over some discrete time, for instance, every 5 minutes. And you know the potential demand weights from each origin to destination, okay? And you know also the expected transit time. Now, given that you want to make pricing decisions, and so you have the pricing that is in each location that you need to make, and you need to make a dispatching decision, which is the number of drivers that you send from a location to another at every time period. The thing is that here, notice you have in that matrix n times n plus 1 components. Why is that? Because I differentiate the fact that you may dispatch drivers from a location to the same location to serve customers, and the fact to leave the drivers idle in a location. So let me give you an example. I don't know if you can read it. I hope so. For instance, here is a simple network with 3 locations. You need to decide what will be the price in location 1, how many drivers you will dispatch to serve customers going from location 1 to location 1, how many drivers to dispatch from location 1 to location 3, location 1 to location 2, and finally, how many drivers you just leave idle into location waiting for future customers. And here are the parameters, so the potential demand weights in location 1, 2, and 3, and the expected transit time. Now, let me add a few assumptions before I describe you the Markov decision process. So to keep it Markovian, I will assume that the transit times, which are random, are exponentially distributed. Also, I will assume that drivers can only be assigned to customers in the same location. Drivers always accept to be repositioned by the platform. And finally, customers that are not served within the periods will opt for site transportation. So they are impatient and they just leave.
Thomas?
Yes.
When you assume transit time are exponentially distributed, how does it affect? Because generally you tend to move your drivers from non-congested areas to congested areas. So it's not sort of a bit very exponentially distributed. It might be another way. So, because now you're sort of assuming an exponential, but generally you move them from non-congested to congested areas. So there should be a sort of distribution for that transit times,
yes,
or not.
And I looked at the distribution, and actually it would look like an airline 2 distribution. So you would have a lot of density for like small transit time, and then longer transit time, it would decrease quickly.
Okay.
But here, yeah, it's an assumption here that we make that it is exponential.
Okay. And that's due to the fact that you're doing Markov process?
Yes.
Okay.
Yes, so I need basically the state to have the Markov property. And so to do that, I need to assume that the transit times are exponentially distributed. Okay, so let me describe how is the Markov decision process. So what is the state first of all? So the state in my case is made of two components. The first one is the number of drivers available in each location. And the second one is the number of drivers in transit between the locations. So the number of drivers in transit are the drivers that are not available currently serving customers or repositioning. And a constraint of the state space is that I also have a finite number of drivers in the network that is equal to F. And so at every time you need to have all those drivers either available or in transit. Now, what about the decision? Two components again. I have continuous prices. And for simplicity, I will just say that it is between 0 and 1 in each of the locations, and dispatching decisions, which are integer numbers, and say how many drivers to dispatch between the locations. Now, a condition is that at every time, the number of drivers that I dispatch is equal to the number of drivers available in the location. Okay, accounting for the fact that I can leave drivers idle in that location. I have three types of random events in the Markov decision process. I have the realized demand that follow Poisson distributions, and those drivers have some willingness to pay, so the rates will vary according to the price. So here is the potential demand rate, and here is the probability that the driver has a higher willingness to pay than the price proposed by the platform. And for simplicity, I will just assume that that willingness to pay is uniformly distributed. Now, about self-relocation of the drivers, I assumed here a very simple rule that will be complexified in the future. But for the moment, it is that rule. It's for further research. So I assume that every time the drivers that are idle, they throw a coin and they decide whether they self-relocate according to the result of the coin, with some probability beta. When they decide to self-relocate, they make the decision, okay, where do I self-relocate now? And that will be a function of the price observed in the auto locations as a function of the price in all the auto locations. So intuitively, you see that if the price in auto location is higher, the driver has higher probability to self-relocate there. But conversely, if that transit time here it's the rate actually is lower, it means that the location is further from the drivers. So the drivers has less incentive to relocate from, I don't know, San Bernardo to Itacula, for instance, even though you see very high price.
Thomas, how you are accounting for the time it takes because you might think of relocating, but you're going to be available on a T plus your driving time. And here you are using the same T's in all of you're supposing here that your location is immediate or not?
So the drivers, when they decide to self-relocate, they will start to transit with exponentially distributed time.
Okay.
But when they make their decision, they look at the expectation of that transit time. So here is the rate, but tau, and they make that decision according to that.
Okay.
They don't know in advance how long it will take, but more or less they have some idea on the expectation. Okay, and so that's for the self-relocation. And finally, a third randomness in the model is that when drivers complete service, they will complete according to binomial distributions. So because it's exponentially distributed, the probability that they complete the service is the probability that they finish before 5 minutes given the exponential distribution. And the number of drivers that can complete service is the number of drivers that are in transit currently, the number of dispatch drivers for the period that you sent, and the number of drivers that decided to self-relocate by themselves. Okay. So here are how the transition function works. So the number of available drivers in time t plus 1 is equal to the number of drivers that you decided to keep idle, which is deterministic, and then the number of drivers minus the number of drivers that self-relocate by themselves, plus the number of drivers that completed their service in between the two periods. Similarly, for the number of drivers in transit, it's the same. It's the number that you had in the period before, plus the number of drivers that you dispatched, plus the number of drivers that self-relocate, minus the drivers that completed their service between the two periods. And finally, the reward function. So it has three components. The first one is for the revenues, which is proportional to the price, the expected transit time, and the number of customers that you serve. So when you dispatch that amount of drivers and that you have that amount of customers that arrive, you take the minimum between the two. Similarly, you have some cost for repositioning drivers, which is so the excess of dispatch drivers in comparison with the numbers that arrived. And it's also proportional to the transit time. And you finally pay some costs for the abandonment of customers that arrived, but that haven't been served by the drivers. Okay, so this is the model basically. Do you have any question about how it works? Was everything clear for you? If yes, yes,
Just that. Maybe I guessed that, but which will be the actual T in the timing for how frequently you will be.
So in that case, it is every 5 minutes.
Every 5 minutes.
But in reality, it would be much smaller. And I will consider larger instances after, like in further research, but for the moment, it's only 5 minutes. Okay. So what we want to do with that model is basically find an optimal policy, which is a mapping between state and action for every time, so that you maximize the expected rewards for all the periods, the sum of the rewards. Now, the problem with that model that you may have noticed is that you have a curse of the known curse of dimensionality. So you have combinatorial state space, you have continuous actions for the price, combinatorial action for the dispatching, but also the possibilities of transitions is huge. So typically you cannot solve it with the usual dynamic programming. And now I will present you a few methods that can be used to solve this problem. The first one, that is plus, is to build a mathematical optimization problem, which will be deterministic, based on the expected value. And you solve that deterministic formulation not for the whole horizon time, but for some future periods in a look-ahead way, and then given the state that you observe. Okay, so here is an illustration. You have that time periods, and you have the expected value program that is solved every 3 periods, and that take the state in the some input, and then guide in advance the price and the dispatching of drivers for 3 periods. And you repeat it over time until you reach the end of the episode. Okay, so what are the pros? It usually runs fast, it's interpretable. The problem is that it totally ignores the stochastic fluctuations in the model because it is in a deterministic setting. And also it's myopic because it only looks some decision times in the future, but not the whole time horizon. Okay, so here is the mathematical problem written. So you see, I try to maximize the revenues minus the cost of repositioning, the cost of abandonment, and the number of customers served, which is the variable EIJT. This is always inferior to the number of drivers dispatched, and the arrivals of customers, which is just the arrival rate. I cannot never dispatch more drivers than I have available in the location. And here you have some flow balance equation. And finally, here you determine deterministically the demands according to the price. So here it would be 1 minus PIT. The only difficulty with that model is that actually here you have a bilinear term right? Because PIT and EIJT are both variables, but using your observers and McCormick envelopes, which you may know, you can solve it quite efficiently for a few periods. Okay, now what is the second approach? You can use deep reinforcement learning methods, and in particular, actor-critic algorithms. So this is like state-of-the-art algorithm, and it works as follows. You have the Markov decision process that gives some state to the actor. The actor makes some decisions according to that state, and then the next state and the reward is observed, and the critic says, what is the value function? Saying to the actor, you did it well, you did it bad, and then the actor adjusts. This is basically the idea. So you have the actor acting and the critic saying whether it's good or not and giving the overall direction. The pros of that is that you have now a policy that can be dynamic. It's based on neural networks, so you can approximate it quite efficiently, even though it can be a nonlinear function. The problem with it is that you have to use a lot of computational power, and usually the solution is sort of black box. You just train your neural network, but you don't really know what happened. You just see the final solution. So here is, for instance, the architecture that I used that can be used in the research. So you have the input that is the system state that goes through several layers for the actor, and then you learn some parameters of normal distribution. Okay, those parameters, mu, for instance, will say, okay, the price is on, that I should take in that state is on average 0.5, but with some variance to induce exploration, which is the sigma in the normal distribution. Then the price will be on average 0.5, but sometimes 0.45, sometimes a bit higher. Same for the dispatching decision, which here is formulated as a percentage of the number of drivers that is sent from location I to location J. For the critic, it estimates the value function. So it's a value. Okay, now what I will present you is the approach we actually used in the paper, and that aims at combining those two simple ideas. Because the idea, the intuition is, we don't want to train a deep reinforcement learning algorithm from scratch. The expected value program already is some good heuristic, and we would like to start from there and then improve, okay, to save a lot of computation and time. So we train the actor and critic to reproduce the policy of the expected value program in the first time, and then we continue learning with normal deep reinforcement learning. And so the pre-training, we will pre-train the neural networks in 3 steps. In the first step,
The critic, it's able to look ahead at the future and see everything, and the actor just only sees it's on the present and does the policy, and the critic is able to foresee all the future.
yes.
Okay, so he critiques according to his view of the future.
Yes, exactly. So the critic estimates the value function. That is an estimate of the future total profit that you can get from the current state. Okay, so now what do we do to pre-train the neural networks? First, we run a simple model expected value program for a lot of iterations, and we store basically all the actions that the expected value program took for every state. So we have a data set of, for instance, 50,000 state action pair. Okay. Now that you have that information, in step 2, for J iterations, you want to minimize the difference between the policy of the neural network according to some parameters and the action that was taken in the current state. Okay, so it's a simple stochastic gradient descent where you want to minimize the mean square error. Then in step 3, you train the critic network. So the actor network already knows the policy to follow according to the expected value program, but you have no idea of the value function for that policy. So what you do simply is policy evaluation. You run the policy of the actor for some time, and you let the critic learn. So this is how we do. We run that policy learned by the actor for L decision times. We store the total returns observed for each time step and the states observed, and then you again minimize the difference between the value function estimate and the total profit from the state through stochastic gradient descent. Okay, so kind of a simple procedure that is actually quite fast. The whole procedure here takes more or less 1 hour, and you will see that it can really do a great job in reducing the computation time.
Are you able to parallelize this process?
I could parallelize it, especially building the dataset. I haven't done it yet, but I will probably try to do it. So that if you parallelize it, it can really be quite fast. Usually building the dataset, it only takes 10 minutes on my personal computer. Okay. So now I presented you the methods. Let me show you some numerical results that we got for that method. So I have some data available from New York City datasets, which is the demand waves and the transit time that I extracted for the peak hour between 7 and 9 a.m. in the morning, February 6th. I have 8 locations and 24 periods, and I have 1,200 drivers. Those drivers decide with probability either 0.0 or 0.1. Those are 2 instances to self-relocate. And the abandonment cost is equal to 1 and the reposition cost to 0.3. Okay, so let's look at the results. Here I plotted the training curve for the normal PPO algorithm, which is an actor-critic algorithm, and the pre-trained actor-critic algorithm. And as a baseline, I have the expected value program that is solved every 4 iterations, which was the best which would get the most, the highest average total profit. So here you see the orange curve and the purple curve are like PPO with different learning rates. And here the expected value program, and here you have pre-trained PPO, which seems to increase slightly in this case. But when you look a bit, you zoom a bit, this is what you would obtain here. So here is a zoom from that same graph, and it continues to learn. It increased the profit by an average of 300, which is in that case like 5%. Okay, it's basically the program learning the stochastic fluctuations. Same can be reproduced in the instance with self-repositioning driver, where you again see the same result. Now I repeated that for like more instances, comparing the computation time and the final performance. And here are all the instances. The only difference is that here I only used 4 locations and a slightly longer time horizon. But here you can see that the computation time overall is drastically reduced. So here the maximum was 90 hours to run the PPO, and you see it hasn't converged yet. While here the maximum was 24 hours. And you see that pre-trained PPO actually converge to higher results than the expected value program. But in the worst case is that using PPO alone wouldn't even converge to a good policy. Okay, I would probably need more time and probably get stuck in some local maxima. And also I want to say that that column for PPO is the result of several attempts to tune the learning rate. Okay. Unfortunately, I had, so here is the results after 5 different attempts to tune the learning rate, but I will not do it forever. Maybe it could converge ultimately, but still, I think that my method is simpler to use. So that's the first case. Now let's look at what it actually does. What is the policy that it learns? So here in the heat map, you have on the y-axis the origin for its location and the destination. You see here clearly that there is the demand pattern So you have all the customers that want to travel to 6, which is midtown. Okay, this is like the sum of the demand for the whole episode. And then here you see the arrivals, which will differ according to the price in each location. And so typically, if you have sufficient supply in orders, you just maximize profits, right? And you would set a price equal to 0.5 because distributed, the willingness to pay is distributed between 0 and 1. But when you have a shortage of supply, you increase the prices. Regarding the dispatch drivers, you see that it follows closely the service of customers. So the algorithm has learned to dispatch the drivers to customers. More interesting is to look at the difference between the self-relocating behavior of the drivers and the drivers repositioned by the platform. So the self-relocating of the drivers here, you see that you have a lot of self-relocation starting from 6. These are like all the drivers that complete their service in 6 and see no customers waiting for service in midtown and relocate to other locations. Now, what is interesting is that in 6, where you have a high price and you will see that there is a shortage of supply, you don't have enough drivers that self-relocate from a location 6. Why is that? Because the transit time is too long. So what is the reaction of the algorithm? It is to dispatch to reposition drivers to that location. So intuitively, the idea is the algorithm observes drivers self-relocating, and then it says, okay, there are not enough drivers relocate by themselves. We will pay some additional to relocate, to make them relocate. So that's it for this slide. Do you have any questions so far?
Here, there's no loss of demand on the process of if a customer does not sort of cancel the trip or anything, the trips are filled everything or not?
Yes. So yeah, I did not model directly the cancellation of drive. Yeah, I see what you mean. For instance, the driver is going to pick you up, but it takes a too long time, and so you cancel it. In that case, I do not represent it. I just say, okay, customers that are matched with drivers, they will be served. But if they wait more than 5 minutes, then they just abandon the platform. Okay. Now let's look a bit at what is going on in the demand. So for each location, I plotted the potential demand, the realized demand, and the fulfilled demand over time. And so you see here the overall increase in the demand in each location, and the fulfilled request and realized demand that can remain stable because you adjust price so that you do not have shortage of supply. Yeah, only if in that case you have sufficient supply, so you see that you have an increase in realized demand. Yes. So about the shortage of supply, it may not be very clear, but for instance, here in location 0, you see that you have that gap between the realized demand and the fulfilled demand after some time, while before it wasn't the case. And this explains why you reposition drivers in that location, why the platform did it. Now, let's look at plots, auto plots, which are the price in each location and the number of available drivers. So now this graph may be a bit misleading because you see that you have that huge drop in the number of available drivers in each location. But actually, I use different scales here. So here you see, for instance, that you only have about 25 drivers available. Here you always remain around 70, 80, which is sufficient to serve the demand. And now you see how the prices adjust. So here you have sufficient supply, so you do not increase the prices. Here you start having that shortage of supply, so you increase the prices. Now you see those spikes, which may seem like the algorithm didn't learn so well, But actually, it is because it closely mimics the demand rate. So if you see here, for instance, oh, oops,
Sorry. Look, oh,
see here, for instance, that price drop here is due to the fact that we have some drop in demand.
Thomas, there's no testing on the demand on the process.
No, yeah.
So here is sort of reacting to the demand, and you're learning by reacting on demand.
Yes, yes, that's a good point. That there is no demand forecast. I could have included it in the state space, for instance, the arrival rate for the next periods. But the problem is that my Markov decision process is already quite complicated. So if I add those components to the state space, it will really become intractable. So I just let it learn for every time period what will be the expected demand. Okay. Now, last point is about the policy robustness. So far, we said, okay, we know the arrival rates, we know the transit times, but what if we apply the policy to 1 week later, for instance? And there you haven't estimated the arrival rates and the transit time, it's totally unknown. And so we tried to do that with data of the next week, and we applied here 3 different policies. The first policy is, in red, is the expected value program based on last week. The second policy is the policy learned by your algorithm, here in blue. And finally, I let run the actor critic algorithm for the next week, having those data available. Okay, so that PPO is kind of cheating because it knows the arrival rates and the transit time. Yet it cannot learn efficiently good policy for the next weeks. So you see here again, it converges to like local maxima. What is nice is that our policy seems to be more adaptive than the expected value program, meaning that it can better adapt to unexpected fluctuations. And finally, because PPO doesn't seem like a good benchmark, I compared the policy for the 7th of February, the 8th, and the next days, in comparison with the EVP having data of the 6th of February, and the EVP that again cheats and see clearly what will happen in that day with and knows the arrival rates and the expected transit times. And so you see that consistently my algorithm pre-trained PPO will have higher performance than EVP, yet it doesn't know the expected transit time or arrival rates, so it will perform less well than the expected value program that knows those data. So that's it. So what I presented you is a Markovian model for joint pricing and dispatching decisions. I included spatial temporal imbalances in the demand, stochastic demand and transit times, and I tried to model some customer driver behavior. I presented you a few approaches based on mathematical optimization, deep reinforcement learning, or the two in combination. And in the future, I would like to train a more robust policy, elaborate more the self-relocating behavior of the drivers, and also try, instead of an expected value program that takes deterministic value, multi-stage optimization. So thank you for your attention. And
Thomas, I have a question regarding, because here you have a learning process. Have you analyzed how the system is learning actually? How different are the initial solutions that your system is generating from the last times, so you can actually even try to have a more enforced learning, more faster? So try to learn, are there any clear patterns or anything that I could induce into the system so it learns faster or better?
I have looked a bit at it. So I was looking at the policy at 1 million time step, 2 million, and so on. What I observed is that basically learning the price to set in every location is way faster than the dispatching. And dispatching is kind of always coping with that because the prices adjust, the demand adjusts, so you change the dispatch. So yes, I guess I don't know if it answers your question a bit.
And in that way, if you increase the time step of your, instead of having 5 minutes, 10 minutes, will it affect the quality of your policy or not? Regarding what
Yes.
Jorge was talking.
So if it would be 1 minute, actually, I don't think it would be quite difficult to find a good policy because you would have a lot of, for instance, the arrivals in every location would be 1, 0, 1, 2, and so on. And my algorithm basically has some issues knowing the exact number of drivers to dispatch. Usually it's sometimes 3, sometimes 1. But if you increase the market thickness and you have, for instance, 100 arrivals, it doesn't matter so much that you have 102 dispatch drivers, right? But if you have smaller time interval, it can really become a problem because systematically you will you will dispatch too many drivers or too few. So for the moment it's 5 minutes. If it becomes 1 minute, for instance, I think the learning process would be much more difficult. Yes, in the literature, usually they take 15 minutes time interval, 10 minutes, 5 minutes, sometimes 1 minute, but then you would actually use more robust optimization and that kind of models.
Questions? No? Thank you very much, Tom. Excellent presentation. Thank you very much for your time. Thank you. Invitamos a todos en la próxima semana a otro seminario. Muchas gracias. Thank you very much, Thomas. Nos vemos. Muchas gracias. Se me olvidó. La casa, ¿alguna pregunta? Thank you very much.
Salad.